this lecture is about firearms. In some countries, firearms are very rare, and those that do exist are strictly controlled, and gun crime is rare. In other countries, ownership of firearms is much more widespread, control is laxer, and gun crime is more common. When we talk about the forensic science involved with firearms, it's really divided into three parts. There's the internal ballistics, which is about what happens while the projectile is still within the barrel of the gun. There's the external ballistics, which is what happens when the projectile is in flight between the gun and the target. And there's the terminal ballistics, about what happens when the projectile hits the target. So what we're going to talk about in this lecture is the internal ballistics. What happens in the barrel and how this affects the use of firearms in evidence. So let's take a quick look at guns, starting with the original guns, the early guns, such as this one here, the Tsar cannon in the Kremlin in Moscow. Early guns are what we call muzzle loaders. That is, everything that has to go into the gun has to be shoved through the muzzle and down the length of the barrel to the sealed end. What muzzle loaders needed was some explosive and a projectile. A fuse would then be lit, the fuse would burn down into the explosive, that would detonate, and then the energy released, the pressure and the temperature from the explosion of that material will cause the projectile to shoot down the barrel at high speed. Guns come in all sorts of sizes, from very, very small to very, very big. Here's an example of what we might consider the first of the superguns. And this is a gun known as the Great Turkish Bombard. And several of these were built for the siege of Constantinople by Mehmet the Conqueror back in 1453. And these were enormous guns, 5 meters long, with a 760 millimeter internal diameter, made out of bronze. They fired cannonballs which were carved out of granite and weighed 680 kilos, and because of the size of the gun, it took a lot of men and a lot of oxen to move the thing around. Well, obviously, you couldn't fire this thing very often, and they were able to fire it 7 times a day. Nevertheless, it was very important in smashing down the walls of Constantinople in 1453. And 300 years later, these guns were still in use by the Turks to protect their city. Since then, engineering has improved. We no longer make guns out of bronze. They're made out of steel nowadays. This means that we can make the barrels much stronger, which means that we can release a lot more energy inside the barrel without the barrel bursting, i.e. we can get much higher temperatures and pressures, and therefore we can fire projectiles much further and much faster. So this is the muzzle loader, and not only did materials improve, but also the design of guns improved. So these muzzle loaders were replaced in the 19th century with the breech loaders. So in a muzzle loader, everything has to be pushed down the barrel. In the breech loader, it's loaded from the breech. This is much more efficient and means that the firing rate can be increased. And nowadays, of course, the loading of a new projectile into the barrel is automatic. A third improvement is the invention of the cartridge. The early guns, like that Tsar cannon we saw, the explosive charge and the projectile were separate and had to be loaded into the barrel separately. The cartridge combines both the projectile, i.e. the bullet, and the explosive, which provides the energy, into a single object. And clearly, loading a single object into the barrel is much more efficient. Well, let's look at these cartridges. Okay, what is the detailed structure of a cartridge? You have to have a bullet. Then behind the bullet is the propellant, which provides the energy for the bullet, and this is contained within the cartridge case. Now, the propellant provides the hot expanding gases which give the kinetic energy to the projectile, and they would be materials such as black powder or nitrocellulose. These do not ignite on their own. There has to be something to make the propellant ignite. And this is a chemical built into the base of the cartridge, and this is called the primer. Now, the primers are shock-sensitive compounds. These detonate when they experience a mechanical shock, and the detonation of the primer then ignites the propellant and causes the gun to fire. Typical primers that are used are chemicals such as lead stiffnate, shown on the slide. So now we know what the cartridge is made of. What happens to each part of the cartridge? Well, the bullet, of course, is shot towards the target, so it will typically be far away from where the firing took place. What about the cartridge case? When the gun is fired, the cartridge case is ejected from the breech, as we saw in the photograph just now. This means that the cartridge case will be lying at the site of the firing, unless, of course, the gunman takes specific precautions. Either he collects the cartridge case after firing, or uses another technique that we've seen a few times now, in that he's firing the gun from inside a sack so that the cartridge cases are collected inside the sack. Usually, however, the cartridge case is at the scene of the firing. Finally, the propellant. What happens to the propellant when it ignites? Well, this is messy. It's turned into gases and particles, and we'll talk about these gases and particles in the next section. Now, we said that the primer detonates, and it's the primer detonation that causes the propellant to ignite. What is the mechanical shock that causes the primer to detonate? It is the impact of the firing pin on the end of the cartridge. When the trigger of the gun is pulled, that releases the firing pin to hit the end of the cartridge, and that causes the gun to fire. The base of the cartridge is made of metal, so when the firing pin hits it, it will leave an impression. And this is the first piece of forensic evidence from firing a gun, the impression of the firing pin on the base of the cartridge. Firing pins are going to be individual. They are going to become worn in particular ways, so no two firing pins are going to leave exactly the same mark. So suppose there is a crime scene where a cartridge case is found. A suspect is apprehended who possesses a gun. The question is, was that gun used to fire the shot at the crime scene? The way this is investigated is that the gun is loaded and a test bullet is fired, and the test cartridge case is obtained and compared using a comparison microscope to the cartridge case found at the crime scene. If those firing pin marks on the two cartridge cases are identical, then it can be concluded that that gun indeed was used. Another technical improvement that was made in guns is rifling. Early guns, such as the Tsar cannon that we saw, have smooth barrels. Rifling is the cutting of grooves along the barrel. These grooves are not straight, but they curve. When the bullet or the shell is fired, it's gripped by those grooves, and that gives it some spin. And this spin, just like the bowler in cricket giving the ball some spin, improves accuracy and the stability of the firing. Most guns are rifled. Some guns are not. For instance, shotguns are not rifled, they fire pellets, and typically homemade weapons are not rifled either. The gun in the picture is a 7-inch gun from Singapore's Labrador Park, and the breech is missing, so you can look down the gun and you can see the pattern of the rifling. What's the forensic consequence of this rifling? The forensic consequence of the rifling is that the grooves and the lands, when they grip the projectile moving down the barrel, leave scratch marks on the side of that projectile. These scratch marks are known as striations. Now, just as every firing pin will be individual, each barrel will also be individual and will leave characteristic striations on the bullet. The procedure is the same. If you have a bullet from a crime scene, you have a suspect gun, you once again reload the gun, fire it. This time you collect the bullet. You compare the test bullet with the bullet from the crime scene under the comparison microscope. If the scratch marks match up, you can conclude that that bullet was indeed fired from that gun. We've said that when a gun is fired, the propellant and the primer are turned into gas and particles. These particles are known as gunshot residue, or GSR. GSR comes out of the muzzle of the gun, it comes out of the breech of the gun, and it will be deposited on anything in the vicinity of the gun when it's fired. It will be deposited on the hands and the clothes of the gunman, presumably not on the palm of the hand because that's on the gun, but on the back of the hand. And it may be deposited on the clothes of whoever is the target. The GSR spreads out to a distance of about 1 meter. So if the victim of the gunshot is 1 meter or less away, then you would expect GSR on the victim. If, however, the victim is really close to the gun, that is, the gun is being pressed against the victim's head, then there's not much GSR on the victim because it's been forced into the wound. So here's a case where the gun is not pressed against the victim's head and the victim will have GSR over him, but pressed against his head, most of the GSR will go into the wound. Now, how can we detect GSR? Most explosives include nitro compounds. So GSR will contain nitrite or nitrate residues. Nitrite residues can be chemically detected by a process called the Grice test. However, the Grice test is not a specific test for GSR, it is a test for nitrite, which means that any other materials that may also contain nitrites will also be positive to the Grice test. And this can be true from fertilizers, it can be true from urine, it can be true from cosmetics, it can be true from tobacco. Over-reliance on the Grice test has caused wrongful convictions. For instance, the case of the Birmingham Six, who were convicted of being IRA terrorists and carrying out a pub bombing in Birmingham in 1974, was based in part on a Grice test, which was subsequently deemed to be unreliable, and in 1991, after a long time in prison, their conviction was overturned. Another test uses a chemical called sodium rhodisonate. Sodium rhodisonate is not sensitive to the nitrite, it's sensitive to the metals in gunshot residue. So gunshot residue may contain salts of metals such as lead, barium, and antimony. So this is sodium rhodizonate, and as you can see, as a solid, it has this dark green color. So what I'm going to do is to dissolve it in water. And it's an interesting material because it changes color when you dissolve it in water. So this is the color of an aqueous solution of rhodizonate where the metal present is sodium. So sodium rhodizonate. But the color will change if we add this to materials that contain other metal compounds, such as the metals that are found in GSR. This is barium. This is antimony. And this is lead. So if you can use sodium rhodizonate to detect these three elements, then you're probably dealing with GSR, because this is a pretty rare combination of elements. But as we know from our lecture on spectroscopy and atomic structure, nowadays we really shouldn't rely on these old-fashioned color tests. We have sophisticated instrumentation to do this analysis. And one of the best ways to analyze gunshot residue is to use SEM-EDX, which we talked about in that lecture. SEM, the scanning electron microscopy component, we can actually see the particles of GSR, which are in the micron range. And this is a GSR particle. The EDX component of the instrument can then tell us what elements are present in that particle. And this can be very powerful forensic evidence. In 1999, the British TV personality Jill Dando was shot on her doorstep of her home in West London. After a long investigation, a man called Barry George was arrested, charged, and convicted. So in 2001, he was convicted of Jill Dando's murder. Part of the evidence for his conviction was finding one particle of GSR in his coat pocket. Now, if you fire a gun, or if a gun is fired at you, and there's GSR deposited on you or your clothes, it's not going to last long. Within a few hours, depending on exactly what is done, that GSR will be gone. So GSR must be searched for as soon as possible after the crime is committed. In the case of Barry George, they were able to find a particle of GSR on him because it was in his coat pocket, and presumably was trapped in the coat pocket and therefore was not washed off in any way. Barry George, however, appealed his conviction, and in 2007 his appeal was successful and he was released. He was considered innocent by the Court of Appeal because the GSR evidence was considered to be unreliable. What went wrong with the GSR evidence? The answer is GSR cannot be individualized. Just because you find a GSR particle which chemically matches any GSR found at the crime scene doesn't mean it's linked, because there's not much variation within GSR. Investigators involved in the Jill Dando case categorized GSR into 5 types. GSR containing lead, barium, and antimony, GSR containing lead, barium, antimony, and aluminium, GSR containing lead, barium, antimony, and tin, GSR containing lead, barium, calcium, tin, possibly antimony, and barium, calcium, silicon, tin, and maybe lead. So if you only have 5 different types of GSR, it means that the individualization is not very effective. So GSR is strong evidence, but on its own is not sufficient. So, arising from the internal ballistics, we have some important forensic methods. We can compare striations caused by rifling between different bullets. We can compare the mark caused by the impact of the firing pin onto the cartridge case. And we can also study the chemistry of GSR. And even though these methods have some limitations, it's still extremely important in firearms cases.